Hi everyone, my name is Muhammad Awais. I'm one of the TAs for ECE241. This video is the tutorial for Lab3, and it is mostly going to focus on the always statement of Verilog. Um, Before we start though, um, Verilog is a hardware description language, okay? That means, well, you already know what that means. It means you have to describe your circuits in the Verilog so you can basically synthesize them and get them to work. There are, however, two ways of describing your circuits in Verilog, and the first is called structural description, while the second is behavioral description. Um, those names are exactly what they sound like. Structural description means explicitly defining what your hardware is all about. It means explicitly specifying the gates, specifying the submodules, building the entire hierarchy from the gates, and so on. Um, for example, this mux, this is a structural description. You can see I have two inputs, input 0, input 1, I have the select, I have the output, but I'm explicitly defining what the gates should be like. I'm saying, I have an AND gate here with those inputs. One of them is the output of an inverter. I have this other AND gate, and then I'm combining both as the inputs for an OR gate, and then this OR gate will give me the output that I'm looking for. You can say, hey, I have this complex circuit, it will use this submodule, it will use this other submodule, and then it will have those gates to combine their outputs and so on. This is explicitly defining what the hardware circuit looks like. It means basically you have come up with the design of the hardware, you have a schematic in your head, and you're just describing what the schematic looks like. That is structural description. The other thing, which was behavioral description, is also pretty straightforward. You can infer from the name what it means. It means instead of describing the hardware circuit itself, you describe the behavior you would expect this hardware circuit to do. That means I would imagine a function. I want this function to happen. I don't know what the hardware circuit should look like, so I will describe what the expected behavior is, and then I will give it to my synthesis tool, which in this case is Quartus. And basically you will let Quartus infer what the actual hardware circuit should be to give you this expected behavior. A simple example for this, again, this is another mux. It has the same interface. I didn't change anything. Input 0, input 1, select, output. You have this always statement, and always statements are mostly used for this behavioral description sort of thing. Let's ignore this part for now. It will be for the next video. Let's focus on this. So this is the core of the always statements. So this is the body of the always statements. This is the behavior that I would expect my circuit to do. Okay, so that behavior is simply the following. If the select is 0, I want my output to be the same as input 0. Otherwise, I want my output to be the same as input 1. Okay, and instead of describing what the mux looks like in terms of gates, in terms of hardware, in terms of a circuit, I describe what the mux should do in terms of a function, and then I leave it to Quartus to understand this code and figure out that, this code can be done by a mux, let's convert it to a mux. Okay, so the behavioral description is basically dependent on your CAD tool, on your synthesis tool, and how good it is in understanding this or converting it to hardware. This means that behavioral description is risky because you run the risk of creating things that are not synthesizable. You run the risk of creating, of describing a behavior that is impossible to convert to hardware. That is the risk of behavioral description, and so that's why you have to understand how behavioral description works in detail. You have to understand how the CAD tool, how the synthesis tool understands behavioral description, how it converts it to hardware. You have to understand common descriptions and how they correspond to, say, muxes, decoders, latches, or flip-flops, and so on. Last warning, you should already know the difference between Quartus and ModelSim from Lab2. Quartus is a simulation tool. ModelSim is a simulation tool. Quartus is a synthesis tool. When they compile your Verilog, they compile it in two different ways and for two completely different purposes. ModelSim takes your Verilog, compiles it to C++, and then uses this C++ to run as a simulation. Quartus will take your Verilog code and then will compile it to an actual circuit that can be installed on an FPGA. The difference being you can write unsensitizable Verilog. You can write unsensitizable behavioral descriptions. You can simulate them in Model Sim. They will work fine. They will give you the correct behavior you're looking for. But when you try to synthesize them in Cortex, they will fail. So again, try to understand what behavioral description is all about. Try to understand how a hardware circuit will be inferred from your behavioral description. And just because it works in Model Sim, do not assume that this is a correct description and that it will work fine in Cortex. Okay? This was just a quick introduction. The next video will show you the always statement in detail. It will tell you what this part is, and it will tell you about things that you should not do here or in the body itself.